So we've got good news on the block on the 383, but we've got some bad news on the crankshaft on the 383. So we're going to go through some of the bad news there and talk about that here in a minute with the cleaning guy. But for now, I want to talk a little bit about the block here. So at this point, block machine work is pretty much done for this build, and it's ready to be cleaned and have cam bearings put in and freeze plugs and so on. We squared up the decks and decked it. If everything checks out, our pistons should be around 5 thousandths in the hole. We got the block rough bored to 30 thousandths oversize, and then I did the honing on it. I actually went and I bought a profilometer, which allows us to measure the surface finish of our cylinders and of our deck surfaces and so on to make sure that we're actually achieving the results with our machine work that we think we are. I went through on this block and pretty much followed a pretty similar process to what we've been doing for years and years, but with a little bit of tweaks and verification using the profilometer. So I'll put a few clips of the honing in here so that we can talk about that a little bit. We'll be finished honing our block for our desired piston to wall clearance in our Sunnin CV616 cylinder hone. Considering the nature of this application, the main caps are installed and torqued, and a torque plate will be used with a head gasket to simulate the stresses induced on the block when the cylinder head is torqued on. We always like to wait to finish the cylinders of a block until we have our pistons in hand. Pistons we're using for this build are an Icon piston from UEM Pistons. They were nice enough to send these out for us to use in the build, so we really appreciate that. Originally we started thinking we were going to use a dished piston, but we decided to go ahead and bump up the compression ratio. These are the FHR series pistons, which FHR is for formed head relief. And basically what that means is the valve reliefs here are actually forged into the piston as opposed to machined after the fact. These are a 4032 alloy that has 11% silicon content. Basically that gives it a little bit better thermal expansion characteristics and better wear characteristics on the skirt. You know, some other things to note here, we have an accumulator groove between the top ring and the second ring, and what that does is kind of give the gases that escape past the top ring a little bit more room to lower the pressure between the two rings and prevent flutter in the rings. They all measured within about 1/10 of each other, and that's 1/10,000th of an inch for those of you who don't speak in machinist terms. But really nice piston here that we're happy to be using, so excited to get this thing going together. The pistons come with some basic recommendations on clearance, and we determined that we'd like this block to come in right around 4 thousandths piston to wall clearance. We'll set up our MC1 measuring center from QMP Racing and dial it in with a 4-inch standard to measure our pistons, taking note of the diameter of each piston on our build sheet within our Phytron Automotive machine shop software. I went ahead and set up our Sunnin bore gauge such that when it reads 0, we've reached our final bore size for our desired clearance. After the boring process from a previous video, we typically have between 3 to 5 thousandths of an inch of material left to remove to hit our final cylinder bore size. As I mentioned, I recently invested in a Mitutoyo SJ210 profilometer that allows us to measure the surface finishes of our machined components here in the shop, and with that comes a huge learning curve, especially with honing. This tool costs a pretty penny, but allows us to measure our surface finishes in the realm of millionths of an inch, aka microinches. I'm not going to pretend that I'm an expert on it yet, as it's going to take time and experimentation to learn what works and what doesn't to achieve the correct numbers for various applications. With that said, for those of you who are truly my peers in the industry, I'm looking forward to your feedback. Our machine is currently set up with vitrified abrasives, which makes it more difficult, but not impossible, to achieve consistent results when compared with super abrasives like diamonds and CBN. I started with a 220 grit stone in the machine, which we generally considered to be our roughing stone. I took my time with it, working to keep the cylinder straight and round from top to bottom, and keeping the load meter reading around 40%. To put it simply for those who are less educated in the audience, the rougher grit allows for quick material removal and leaves a rough surface finish with sharp peaks and deep valleys. I brought the cylinders basically to the final desired size with this stone. At that point, I switched over to a 400 grit, which is a much finer abrasive. With the 400 grit, I made approximately 10 strokes in each cylinder, keeping the load meter very low, reading around 20 to 30%. With this few strokes at this light of pressure, the diameter stayed virtually the same. Again, simply put, this process begins to plateau the peaks of our surface, giving a smoother surface on top for the rings to seat on. This still left our peaks in the range of 20 microinches, a bit high, so I finished the process with 15 strokes of a plateau brush from Goodson in each cylinder. On average, this left our peaks, or RPK, around 13 microinches, our core roughness, or RK, around 46 microinches, and our RVK, or valleys, around 50. These numbers fall right into what I've seen recommended for this type of application, and after consulting some peers who I trust and respect highly, I determined this would be good for this engine. Of course, as time goes by and I gain more experience and more education, I should be able to modify and improve these parameters as needed, but I was more than happy to find out that our general process we had been following was yielding ballpark results to suit our applications. I am looking forward to using this tool to make improvements to the work I do and further improving our capabilities here in the machine shop. Anyway, really happy with the block. So from here it'll get a final wash and cleaned up, and we'll go through and kind of do our final checks and everything and get the freeze plugs put in, get our oil plugs put in, and cam bearings, and go from there. All right, so now for the bad news on the crank. Are you going to take the blame for this, or do I got to?
I think it's shared experience.
Okay.
Well, we should have mic'd this crank as soon as we took it out of the box and verified journal size and everything, but we just assumed a brand new crankshaft, everything should be good, and we went ahead and did our balance. And after the balance was done, I wanted to come back here and do one last polish on it. Now that we were done doing anything, we might, bump a journal and make a burr or anything. So I set it up here in the crank machine, getting ready to polish it, and started miking the journals, and I don't like what I'm finding on size. It's a little bit on the small side from where I thought it would be, plus we've got one journal here that has bad taper in it. I can't believe it got sent out that way. I'm almost wondering if this crank had been sold to somebody else and they messed around with it and possibly did a bad polish job on it and boxed it back up, and it got returned as a new crank. No one knew the difference, and then we ended up with it being shipped to us, and I get ready to use it here and find out things are not what they should be.
Would it run?
It would run. Probably never ever get any trouble, but it's not
to our spec.
Yeah, it's not to our spec for what we're trying to build here. Quite honestly, even if this was just a stock motor, I would probably want to grind this crank and make it as good as I possibly could, because it does not meet what I would consider to be a good crankshaft for even a stock motor. When I mic this crank, the bad journal here, if I go clear over on this side here, I am 2.0994. As soon as I move about to the middle and all the way on across the rest of the way, 2.0988. So we've got 6/10 thousandths of an inch difference from it's about half of the number 3 journal, and then from there on over it drops down in size.
It's not really even taper, it's more like a ledge.
It's almost like 3/4 of the journal is ground to the small size, and then just this side over here is the correct size that matches all the others. So anyway, at that point, normally I would just set the crank up as a means to rotate it here so we can use our polishing belt. But after I started seeing that, I thought, you know what, I'm going to set up the Arnold gauge here, and I'm going to check this a little bit closer and see what we really are finding here.
Okay, so you've dialed in that journal.
Yeah, so anyway, I've set the crankshaft in here, much like if we was going to grind it. I've dialed in on the number 1 journal. You can see there I'm not perfect on that journal, but I'm darn close to running through with it. So now let's see what our Arnold gauge shows us on here.
Crash. The way this gauge works, that's an Arnold in-process grinding gauge.
Right.
So this is what you would use while you're actually grinding the crankshaft.
Yeah, it rides 3 places around the journal with the top foot here connected to the indicator so you can see what's going on the diameter of that crank. I'm not impressed with that. We've got, what would that be, close to 3/10 odd around on that journal. For me, when I'm grinding the crankshaft here, if I can't get this thing down to where I have less than a couple tenths out around and a couple of tenths across that journal, it really bothers me. I start kind of double checking my machine and my setup, because I'd like to have it come in as perfect as possibly can. I mean, there is no such thing as perfect, but you always strive to have it as good as you can get. Let's move over to the next one here. Machine here, I loosen the chucks and I rotate this, snap in. That's exactly 90 degrees. I check my next journal here. And again, same thing, I'm swinging. So I'm going to index at another 90 degrees here. Same thing. We all have this out around going on. So I'm going to go to the far right, and I'm going to set this as close to 0 as I can get it. And actually right there, we're not too bad on the out around.
Which is the side that by the micrometer is
the right size. Let me just move over to the
move it over.
middle here, and it's just like all of a sudden it drops off there. Move there, it just jumps.
Yeah.
There we're on 0. As soon as I move on the other side of the oil hole, jumps a half thousandths, and then pretty much continues. It's just like there's a step in that journal. I'm not happy with that at all, but we've already balanced it. So we either go with another crankshaft and start over with our balance, or I can grind this one 10 under, correct all that, go back and touch up our balance again. Shouldn't change much, but it may change a little bit.
Or what we decided to do is we have a new crank here to check out and see if it's better to start with.
Yeah, so let's check it, see how it compares to this one. And maybe at that point we'll decide, are we going to grind this one or are we going to use the new one out of the box?
So this is another, exact same crank, same part number.
Same part number.
So you've dialed in number 1 journal there.
Number 1 journal's dialed in. And I've kind of already checked this crank before we turned the camera on there. And it measures pretty straight across. There's a little difference in it. That's probably a strong 20995. They're all measuring real close. I'm not seeing with the mic a lot of taper across there. That other crank looks to me like somebody has been on it with a polishing belt and has kind of goofed the journals up on it. I'm pretty sure somebody had that out and messed with it, boxed it back up and returned it, and then we got stuck with their return. So as you can see there, we've got maybe about 2/10 out around. And you were looking there in a Clevite book. What did they?
Clevite actually lists 1/1000ths, up to 1/1000ths out of round.
Really?
Which sounds terrible.
They also, on a crank like this, we have a range tolerances from the low side to the high side is 1/1000ths.
Yeah.
So like you were saying to me earlier, if the low spot is on the low side and the high spot's on the high side, that would give your 1/1000ths out around.
Yeah.
And I would never try to run a crank like that, certainly one like this. This one, I don't know, you can see there a couple tenths, and it's pretty much even all the way across. It's not tapered like that other one was.
Yeah.
That journal is just next to perfect. This crankshaft out of the box definitely will pass, maybe a couple tenths there. Yeah, certainly no more than a tenth or two taper and a tenth or two out around. I see no problem putting this crank in and running it.
If we want to use this one, we have to completely redo our balance.
Right.
Which, is part of the job, but it also leaves us with a crank that has already been dicked with, because we're going to do another 383 build, basically.
Right.
We have some extra parts here, we're going to go through, but theoretically would already be pretty close if we just grind that crank. Yeah. Everybody's been telling me I need to give the cleaning guy a raise or, throw him some kind of party or something. So I'm going to
So
challenge
we're
you.
going to have a crankshaft grinding party?
Yeah, exactly. This is going to be fun for
Oh,
you.
a pizza party.
No, this is going to be fun. It's going to be a fun challenge for you. I'm going to challenge you. What we're going to do, we're going to measure all of our connecting rods. We're going to put the bearings in. We're going to measure our main bores with the bearings in. I'm going to challenge you to grind the other crank and hit our tolerances and give us a better crank at 1010 than what this one would be standard.
You think I can do that?
I don't know. You seem to think you can.
I'm sure I can do a crank equally as well as this one is. That other crank, there's no way I couldn't do better than that one is unless I just flat crashed the crank grinder into it. But yeah, I'm up for the challenge.
Okay.
Let's put the bearings in the block, torque them all down, make our measurements, put the bearings in the rods, torque them, measure them, and let's grind a crank to match, to hit our specs, which would be better than just putting this one together with standard bearings anyway and just hoping for the best.
Yeah. So it'll actually come out to be a better product. It'll be a 1010 crank. 10 thousandths does not make any difference on the performance of it or the longevity of it. And we're already going to be pretty close on balance, but we'll put the bob weights back on and spin it and touch it up if it needs.
Yeah, sounds good.
We're not going to do that in this video.
Yeah, it's 3:30 Friday afternoon.
Yep. Which is better than when I
3:30 Sunday night.
2:30 in the morning, Sunday morning, when I filmed the last one. But that's what we're going to do, and stay tuned for the next video.
See you guys.